Now we're going to take a look at two examples in this video. The first example is about a rocket and a radar system. And the radar system observes how the rocket moves and the way that it observes. And this is narrowed down to a two-dimensional problem. It's a three-dimensional problem, but let's say that it's working on a plane, and therefore the only direction of motion of this radar system is a theta rotation, and it captures where the rocket's mass center is, and this is defined by this R. So the way that the radar system works is kind of like a polar coordinate system. And we know the rocket moves in the vertical direction with a velocity and acceleration in the same direction. And what is asked here is when theta reaches 60 degrees, the other corresponding measurements are given as r 9 kilometers, and in an actual case you would expect this. You would expect to measure this r. R double dot is measured as 21 meters per second squared. Well, this is just for the question. Usually you would get obviously r dot for you to also receive this r double dot. But this is just for the question. And theta dot is measured as 0.02 radians per second. In a practical case, yes, you can measure this, but also you can measure theta double dot. That's if you can measure theta dot, you can measure theta double dot as well. In any case, this is our question, and we are asked to calculate the magnitudes of the velocity and acceleration of the rocket. And we know the velocity and acceleration of the rocket is in the vertical direction. Now this is 60 degrees, and r is given to us as 9,000 meters, 9 kilometers, and r double dot is 21 meters per second squared. Okay, now let's remember the velocity equation in terms of the r theta coordinates. We had this velocity vector to be equal to r dot er direction plus r theta dot e theta. Now, what do we know about these? We don't know r dot. What we know is r and theta dot. That's good if we know this at least, because at the end of the day, I know theta is 60 degrees. So if theta is 60 degrees, this is the er direction, and this is the e theta direction. If this is 60 degrees, then this is 60 degrees, and here it is 30 degrees, right? And this is not looking that nice, but this is also 60 degrees in that sense. Okay, so what I can calculate here is r theta dot. So I can calculate the component of this v vector at e theta, and I know the angles here, so I can actually calculate this part as well. So what I will do is multiply r times theta dot, and that would be equal to 9,000 times 0.02, so 15 180, I believe, and that value is meters per second, is this component, and as a result of that, if I know e theta, actually I can calculate the velocity. That will be r theta dot over cosine 60 degrees. Okay, that will be the magnitude of the velocity. If I'm interested in ER component, so that I can actually find r dot, then what I could do is, if this is r theta, then the component of r theta times sine theta, sine, not theta, but let's change that to 60 degrees, sine 60 degrees, would be equal to r dot times sine 30 degrees. or you could call this as cosine 60 degrees if you look. Okay, it's the same. So if this is cosine 60, then our theta times tangent 60 degrees will be equal to r dot. So now we have calculated r dot. Now for the acceleration, what we have as the acceleration formula is a to be equal to r double dot minus r theta dot squared er plus 2r dot theta dot plus r theta double dot e theta. So far, what do I have? What I have is r dot calculation. Theta dot I know, r I know, theta double dot I don't know. Okay, let's move back here. I know r double dot, I know r, I know theta dot. So that means I can calculate this component already, which is AR component. If I can calculate the AR component, then the acceleration's magnitude is equal to the AR component over cosine 30 degrees. So that's the solution basically. Now if you're interested in theta double dot, which is not given here, then you can go ahead and then do the similar things to find the A theta component from AR component, and then you can find theta double dot if you like. Okay, so if you're interested in that, you can ask me during the lecture hour. So let's move on to our next question, because that's it basically. You have the numerical solutions right over here available to you guys. I did make a okay, that's it. Our theta dot by cosine 60 and 360 meters per second is the velocity, and then for the acceleration we calculate the AR component and AR over sine theta or cosine 60 degrees, and then you get 20.1 meters per second squared for the acceleration. The next question is a well-known mechanism. It's called the CAM mechanism. It's used a lot in the industry, and you can do a lot with this basically. You can do some timed operations. How it works is that you have this path already defined, and there's a pin that follows this path, and the way that this pin follows that path is that we have the slot here, and then the slot is rotated. Sometimes the cam itself is rotated, so this light blue part is rotated, but in this case the slot is rotated, and then this pin is pushed by the spring over here, there is a spring, onto the path, and it follows the path. And the path, the limaçon, is defined by this formula. Okay, so you can devise your own formula for your own CAM mechanism. In this case, the formula is r equals to b minus c cosine theta. B and c are some constants, and b is greater than c, and therefore we get this shape. Otherwise, you don't get that shape. And r really defines our distance from point O as it rotates, and we can define this theta angle here. Again, we have this r theta component, so you don't need to really work with the rectangular coordinates or empty coordinates. This is already in the polar coordinates, so we can resolve this question in the polar coordinates. The cam does not rotate, that's what we said. What rotates is the slot, and the magnitude of the total acceleration is asked for A, which is the pin over here, in terms of theta, if the slotted arm revolves with a constant clockwise angular rate of theta dot, which is called as omega, and then as a result of that, omega dot is equal to 0. Okay, so that's what we need to keep in mind. What we need to do is, this is the position equation for r, For the velocity, let's remember what we had again. There was r dot er plus r theta dot d theta. Okay. What is asked for us is the acceleration. In the acceleration term, we have r double dot minus r theta dot squared er plus 2r dot theta dot uh, plus r theta double dot e theta. That means we need to calculate r double dot and also r dot. That means I need to take the derivative of this with respect to time. Okay. So p is a constant. The only variable here as a function of time is theta. We'll get the derivation of this one as the first derivation. Let me just do it for you guys. R dot is equal to c sine theta theta dot, which is omega basically. And then you take the derivative of this. There's two variables now. There will be cosine theta and another term with omega dot. And then theta dot is just theta dot. Theta double dot is equal to 0. So in this acceleration term, this term goes away. We will have our double dot term, however. And if you do the necessary calculation, this is already available to you. I don't want to repeat the same things over and over again. And what we're looking for is that this term is gone because theta double dot is equal to 0. The first derivative of r dot is c omega sine theta. If you take the derivative of this, you will get two terms. One term is theta double dot. However, theta double dot is equal to 0. This term is gone. And the other term is the derivation of sine theta. We get cosine theta times omega. So there is this omega squared. So instead of that, we could write omega squared. There's c omega squared. And the next thing you have to do is write out this as r double dot. This part is r omega squared term for AR. Okay, for a theta, we need to only write out r dot, 2 times r dot, this is the r dot, times theta dot. Theta dot is omega, so we get omega squared for this term. And then the magnitude of the acceleration is s, so we need to square these up and add them up, and as a result of that, we get this result. So this is quite straightforward term, but the only thing that you need to remember are these formulas, how you use these. We have the equation for r, so we need to take the derivative of that to get r dot. One more derivative, we get r double dot, and we substitute these in the necessary parts of the equation, so it's quite straightforward in that sense.